Hello, this is a talk about space-time foundations. It's called Collapse of the Manifold. I will start by reviewing definition of space-time, and then I'll go on to a critique of the consensus ontology, which is based on a single shared 4D manifold. And I'll say a little bit at the end about quantum space-time. So what is the idea of a single manifold? There's an idea that space-time is analogous, not the same, but analogous to the surface of the Earth, with a form of locality in space-time which is analogous to spatial locality. So what I mean is single manifold ontology incorporates concepts like this. A set of points with neighborhoods, smooth geometry, and some version of locality. The problem for space-time is that this single manifold idea is in conflict with EPR, Einstein, Podolsky, Rosen, Bell non-locality, both theory and experiment as a conflict. And so there's something wrong with the manifold. What I'm proposing is something wrong with the manifold idea. Nothing wrong with quantum mechanics. So let's investigate that. So here's one definition of space-time from Hawking and Ellis. In this definition, space-time is a collection of space-time events, and there's a smooth 4D manifold with a Lorentzian metric. It's also a Hausdorff space, which is a topological space where points have neighborhoods. I'll say more about this in a minute. And also there's a diffeomorphism, which is topological equivalence between pairs, manifold metric pairs. So there's actually a whole equivalence class of pairs of manifold and metric. More about this later in a minute. Here's a different definition, which I won't go into, but I find this one useful also. This one says space-time is a 4D topological manifold with certain properties, including a smooth atlas, which is a set of maps. So what's the... well, first of all, let's say something about diffeomorphism. Topological equivalence, which is diffeomorphism, is not equivalent to physical equivalence. So here's an example of the human brain. Manifolds have coordinate maps, and in this case that's the coordinate system for the human brain. A diffeomorphism is the mapping of one manifold to another. So a smooth atlas is a set of overlapping coordinate maps that cover the manifold. So the point about diffeomorphism is that it gives us the topological equivalence of this type of manifold, smooth manifold, and preserves topology. But it doesn't imply physical equivalence. So there are obviously many different physical brains, even though they can be mapped to one another. So this is really a key point in this talk, that topological equivalence isn't the same as physical equivalence. So diffeomorphism in space-time, there are many topologically equivalent manifold plus metric pairs, equivalent manifolds, but again, topological equivalence doesn't imply physical equivalence. So there are many physical spaces. This is what I'll be arguing for, many physical spaces, not one. So GR is heavy on topology, but topology is deliberately weak. Topology just tells us certain aspects about our physical system, but not everything. So that's an important point. So what about the ontology of space-time? Well, the consensus ontology is really based on this idea of a single 4D manifold of space-time events. The other manifolds, which Hawking and Ellis mentioned, are ignored because they're topologically equivalent, or that's the argument. So we have this 4D concept, which 4D entity which can be curved, can vibrate, And conventionally, the idea is that different observers may have different labels, so you may have different versions of your manifold, but underlying there's a single 2D manifold. That's the conventional idea. But what's the justification for it? So I'll do more of this in a minute. And the problem, again, I repeat, the problem is that the single manifold idea is in conflict with quantum non-locality, which is experimentally proven. So let's look a bit more about definition of manifolds. Points in manifolds must have neighborhoods. So to define a neighborhood, you need some concept of closeness between points. Not a full metric necessarily, but some form of closeness. So with the closeness, you can define a neighborhood, which is an open set of points, and then from that you can go on to get your topology and get your manifold. So the idea is like this. You have a point X, another point Y, and each of these points has its neighborhood. It's the neighborhood of X. And Hausdorff space just means you have these neighborhoods and you can draw a dotted line between the two here. They're disjoint. So example of Euclidean geometry. We can measure and compare distances between points, and this is an invariant measure, delta r in this case. And smallness of delta r is used as a criterion to define neighborhoods. So if we have a point P, we can see is it in this neighborhood or not based on the delta r. So the neighborhoods can be defined in an invariant way because everybody agrees about the delta r. Therefore, Euclidean manifolds, such as this one, can be defined in an invariant way, and there's no problem. So everything is straightforward for this case. But this case is different. A space-time event does not have an invariant neighborhood. I say that because we measure distances in space-time by an observer who measures delta r and delta t, and these individually, of course, are not invariant. And the way neighborhoods are defined in GR is delta r has to be less than some limit, and separately delta t is less than one limit, less than a certain limit, centimeter, picosecond, whatever. So neighborhoods in relativistic manifolds are specific to the observer. And this I want to relate to physical inequivalence I mentioned previously about the brain. So I'm claiming it's impossible to define an invariant neighborhood, or define it in an invariant way for a space-time event. But you can do this for the surface of the Earth. You can't do it for 4D space-time. And therefore, if you can't define your neighborhood in an invariant way, you can't go on and define your manifold in an invariant way either. So if you can't define your invariant manifold in an invariant way, the concept of an ontology based on a single manifold fails. You have no basis. Some additional points to support these two claims. Coordinates are used in GR in the way that I just showed. In GR practice, coordinates are used, delta r, delta t, to define neighborhoods, regions of space-time, volumes, hypersurfaces, whatever. Sorry, you can't draw a diagram of 4D Hausdorff shared 4D Hausdorff space-time manifold using only invariance, delta s, a space-time interval, because you're not allowed to use a time axis or particle word lines, because using this defines a reference frame and defines the observer. So you can draw many diagrams of manifolds, but if you take away the observer, you're in trouble. You can't do it. The same point here, really. Why didn't we use delta s to define closeness, and then we would be directly analogous to the Euclidean case? It doesn't work. If you consider that all points on the light cone are at distance delta s0 from the origin, so if you try to draw a geometry based on delta s, all points on the light cone have to will have to collapse to the origin of the light cone. But points can lie on multiple light cones. So you've got points collapsing to multiple other points. So it doesn't work because you'd have a 2 point, or 1 point would be at 0 distance from 2 other points which are not next to each other. So it doesn't work as a geometry in the normal way. So delta S doesn't give us proximity or closeness in space-time. A different point is that there is actually some missing geometry from the 4D manifold. There's some missing space-time geometry, and I'm talking here about gauge structure. You have diagrams like this in gauge theory where you have space-time, so this bottom plane here, and at each space-time point there's additional structure, which are this gauge fibers. This is a geometric diagram, right, which we couldn't do up here, but this is a geometric diagram. So this is space-time geometry, and this really ought to be included in our idea of space-time. And using a single manifold, you can't do that. So what's happened, we can make the same point slightly differently. We can have observer-specific manifolds, and all of GR is based on using this. And you have your smooth manifold, it's no problem. You've got your coordinates, your manifold, map between different manifolds if you want to, it all works. But we've got a brick wall here, separately. We also have our causal structure, which is truly invariant, shared, and invariant quantities like delta S and many others. But these two are different things. What you can't do is say, oh, I'll have a shared smooth differential manifold. You've got to pick one. And what's happened is these are sort of got conflated, and the idea that we have a shared, these sort of diagrams imply that we've got a shared smooth universal manifold, whereas we don't. We have shared causal structure and we have smooth manifolds, but we don't have both together. So some conclusions. The single manifold in classical physics, it's sort of okay as long as you understand that your single manifold view is for a specific observer only. And that's actually okay in classical physics. So that's why GR works classically. In quantum physics, the single manifold has long been a problem because it implies, the single manifold idea implies locality, and locality is in conflict with quantum physics. So eliminating the single manifold really helps quantum physics. So now I can draw my boxes in green, not in red. So by eliminating the idea of a single manifold, we eliminate the conflict with quantum mechanics, because we no longer expect quantum mechanics to be local because we don't have a single manifold. And the locality idea came from the single manifold. So what I've been really doing so far, I've been criticizing the conventional way of thinking of space-time. So what's the alternative? Many spaces sort of approach. So in a relativistic world, we have multiple inertial observers, and they all coexist. And this argument is really works from special relativity as well as GR. Each observer experiences a physical space. We all see a physical space. So there are multiple coexisting physical spaces, which isn't really captured from a classical viewpoint, where you take one view at a time. And so these multiple spaces are not merely views into a single space, but they are actually separate spaces, which is what I'm claiming. That's the basis of what I'm claiming, but I can't really go into that. I don't have time, but that's the idea. So to conclude, topology shouldn't be directly equated with physical reality. With ontology, you need some interpretation. For quantum space-time, atoms and photons in space, the single manifold actually fails, and so an ontology with multiplicity is necessary, such as a multiple space concept as I've described here. Thank you.